Now let's look at parallel and orthogonal planes. Two planes are parallel if their normal vectors are parallel. So if you look at two vectors here that are parallel to each other, take their normal vectors, they will also be parallel to each other. So if their normal vectors are parallel, that means that they're multiples of each other. Remember, two vectors are parallel if one's a multiple of the other. That means n1 would equal to some number k times n2. Now look at two orthogonal planes. So we have two planes here that are orthogonal. They make a right angle with each other. Then if you look at their normal vectors, so we have a vector n2 and a vector n1. If the two planes are orthogonal, these two vectors will also be orthogonal. So n1 dotted with n2 must be 0. So two planes are orthogonal if their normal vectors are orthogonal, which means the dot product of the normal vectors will be 0. Which of the following distinct planes are parallel and which are orthogonal? To determine this, look at their normal vectors. The normal vector for Q would be 2, -3, 6. The normal vector for S would be 6, 8, 2. Now, any multiple of these would also be a normal vector. But this is the easy one by just reading off the coefficients. N sub R would be -1, 3/2, -3. And the normal vector for the plane T would be -9, -12, and -3. So if the normal vectors are parallel, then the planes were parallel. If the normal vectors are orthogonal, then the planes were orthogonal. So first look at NQ. Well, if you tried to see if NQ and NS were parallel, that would mean that NS would have to be a multiple of NQ. If you multiplied NQ by 3, you would get the 6 in the first component, but multiplying the -3 times 3 would give you -9, and that means that NQ and NS are not parallel to each other. So they're not parallel. NQ and NR. If I were multiplying NR times -2, I would get the first component of NQ. So -2 times NR would give me the first component. So now let's see, -2 times the second component here of NR would give me a -3, and -2 times the third component would give me a +6. So NQ is just -2 times NR, which means that those two vectors are parallel to each other. So NQ is parallel to NR, which really means that the plane Q is parallel to the plane R. So now let's check NT and NQ. Let's see, to make for NT to be a multiple of NQ, I could multiply NQ times 4. That would get the middle component. I'm trying to pick the one that would give me the easiest value to consider. -3 times 4 would give me the -12, but what about 4 times the 2 does not give me the -9. So NQ is not a multiple of NT. So those two are not parallel to each other. So the only ones parallel with NQ then would be the NR. So Q and R are parallel. So now let's see about perpendicular. NQ and NS, are they orthogonal? So that's the question here. Orthogonal is just, this is a notation for that. To be orthogonal, that means that the dot product would be 0. the dot product would be 2 times 6 plus negative 3 times 8 plus 6 times 2, which is 0. So if NQ dotted with NS is 0, that means that Q is orthogonal to the plane S. Well, now let's check NQ and NT. Finding the dot product, we would have negative 18 plus 36 minus 18 is equal to 0. So that means Q is orthogonal to P as well. So Q and R are parallel. S and T are both orthogonal to Q. Well, if S and T are both orthogonal to Q, then that would mean then that S and T are parallel to each other. So let's see, one of them should be a multiple of the other one. There's none of them are going to be real simple to check. Let's look at NS and NT. So if I took NS times a negative 3 halves, it should give me NT. I can get that by just taking the first component divided by the second component and reducing. So negative 3 halves times NS. So if I took negative 3 halves times NS, divide by 2 first, that would be negative 3 times 3, 4, 1, which would be negative 9, negative 12, negative 3, and that is NT. So we do have that S and T are parallel to each other. So we have Q and R are parallel, S and T are parallel, Q and T are orthogonal, Q and S are orthogonal, but since R is parallel to Q, that would also mean that R was orthogonal to S and R was orthogonal to T. Find the equation of a line of intersection between these two planes. Now, to find the equation of the intersection of the two planes, we need to find two things. We're looking for an equation of a line. The equation of the line requires a point on the line and a vector that's parallel to the line. So remember, the equation of a line was given by x equal to x naught plus at, y equal to y naught plus bt, and z equal to z naught plus ct, and that's where the point x naught, y naught, z naught is a point on the line, and the vector v, which is abc, is parallel to the line. So we're going to call the line that represents the intersection of these two planes just script L. Okay, first notice that if you look at the normal vectors, the normal vector associated with the plane Q would be 1, 2, 1, and the normal vector for the plane R would be 2, 1, negative 1. Now clearly those aren't multiples of each other, so these planes are not parallel, so we do know that they will intersect in a line. Okay, so now we need to find two things. We need to find a point and we need to find a parallel vector. So to find a point, now there's many ways to do that. One way is to just look in one of the planes. So I'm going to look in the XY plane, which means that the Z coordinate would be 0. And I'm going to look at what it's called a trace, what that line would be going through the XY plane where this plane intersects it. So if I let Z equal to 0, I would have the line x plus 2y equal to 5. That's for Q. and I would have 2x plus y equals 0, plus minus 0 equals 7. So that's the two equations of the line where the plane is passing through that xy plane. So now what I can do is to find where these two lines actually intersect. And to solve the system of equations, I'll multiply the top equation through by -2. Keep the second one the way it is. You could also use substitution. And now add the two equations, and I have minus 3y equal -3. So that means that y is 1. Now put your 1 back into either one of the two equations, and you'll have 2x plus 1 equals 7, or 2x equal to 6, so the x is equal to 3. So we had z was 0, y was 1, and x is 3. That gives me a point P on this line L. So that would be 3, 1, 0, x, y, z. Now I need to find a vector that is parallel to this line. Now look at the normal vectors. This blue, the blue plane here, Q, has a normal vector, n sub q. And the plane R has a normal vector, n sub r. If those are vectors that are orthogonal to those two planes, then if we have a line passing through either of those two planes, which L passes through both of the planes, any line or vector in the plane must be perpendicular to those two normal vectors. So any vector in R will be orthogonal to NR, and any vector in Q will be orthogonal to NQ. So that means that the line L, which is in both of the two planes, the vector coinciding with that line must be orthogonal to both n sub r and n sub q. So I want to find a vector v parallel to the line. And we'll note that v is orthogonal to both n sub r, so that means that the dot product will be 0, and v dotted with n sub q must also be 0. But because it's orthogonal to both n sub q and n sub r, that means that v, we can find a candidate for v by taking the cross product. So find n sub q cross n sub r, and we will have a vector that's parallel to v. So n sub q and n sub r, place in a 3 by 3 determinant, I times the determinant 2, 1, 1, negative 1, minus j plus k times the determinant 1, 2, 2, 1. That gives me negative 3i plus 3j minus 3k. So the vector that's parallel to the line L would be negative 3, 1, negative 3, or negative 3, or any multiple of that. So we could use negative 1, 1, negative 1. So now the equation of the line. Now we have two ways we can write it. I had it written parametrically up here. This is the parametric form for it. You can also write it in vector form. by saying that the equation R of t would be x naught, y naught, z naught plus t times ABC. Remember, R of t is just the x, the y, and the z of t. And so looking at each of the components is actually giving you that parametric form. So writing the equation of the line, we have R of t, the x naught, y naught, z naught is 310 plus t times -3, 3, -3. This is the representation of that vector valued function. The t values for the equation of the entire line would be from -infinity to infinity. So if you took any t value and plug into this, you will get a point that will be on that line. Okay, and in parametric form, it would be x equal 3 minus 3t, y equal 1 plus 3t, and z equal minus 3t. So that's just pulling each of these three components out as separate values for the x, the y, and the z. So either of those two forms, is the parametric form or this is the vector form, vector valued function form.